Okay, in this video, we will look at the mechanism of sleep. So, in last class, we have discussed about critical shear stress. So, we are writing down the critical resolved shear stress theoretically and by experiment of different materials. Okay, so this is in gigapascal and this is in megapascal, and its ratio. You can see that this copper, this has got an FCC structure. Theoretically, it should have been 12 gigapascal, and iron, it has got a that is alpha iron, that is a body-centered cubic structure. It has got 7 gigapascal theoretically, and zinc, that is hexagonal closed pack structure, it has got 5, and but experimentally, it has got only 15 megapascal and zero point 0.5 megapascal and zero point 0.3 megapascal. So that means if you compare the ratio, it is 800, 14,000, okay, and somewhere around 17,000. That means theoretically critical resource ratios should have been this high, but practically that by experiment it is very low. What may be the reason for this? So why are real crystals so weak? Crystals so weak compared to the compared to the that means sleep takes place much more easy. So in order to understand, we need to study the mechanism of sleep. What is happening at the atomic level? That will be explained in this video. In this video, we will look at the mechanism of sleep. So far, we have discussed what is sleep and how it occurs. So let us start with the definition of sleep. Here, in a sleep, what happens is that one part of a crystal slides over other part, other part on a plate called slip plane. It is called a slip plane. So it is different for different crystal structures. In a direction, which is called slip plane. It is called slip direction. It is called slip direction. So if I draw a figure, it will be like this. Okay. That means there is a slip plane. So slip occurs like this. Okay. Okay, so this is how slip occurs. So this is the slip direction, and the plane on which the slip occurs is called the this slip plane. Okay, so these are the slip plane. Okay, so this is all about slip. Now let us look at the what is a bond change. Let us look at an atomic level. What happens to the sleep? So that means we'll investigate the atomic structure here. So that means if you look at this atomic structure, you can see that see this is how a crystal structure looks like. So this one is so let us draw it like this. So this is how the structure is. So I am drawing various planes of atoms here. You can see these various planes of atoms. So from here, this is the first plane, second plane, third plane, fourth plane, fifth plane. There are bonds between all these atoms here. One, two, three, four, five. These are the different planes. See, for slip to occur, I need to apply a shear stress. Okay, so that means with respect to the bottom, I am applying a shear stress. So here, so let me consider this plane here. So applying that means I'm stress here. Okay, with respect to this plane, I am applying stress. So what happens? See, this causes these atoms to see when I apply a shear stress with respect to this bottom, say along a slip plane. So that means this is a shear stress, and here you can see that in this plane the bond breaks up to here. Draw it a better picture. You can see that this bond breaks up to here. So what happens when the bond breaks here? So these planes, so one and two plane of atoms, so its bond is broken. So when I apply a force, I push these two plane of atoms towards the right side. Right? It moves towards the right. So let us draw that. Okay, here you can see this will remain just like that. So it is one, three, four, it is one, two, three, four, five, right? And so when I push these two atoms towards here, so this plane will be pushed to here. Okay, this plane will be pushed here. Okay, so here it will be pushed to here, and here these atoms will also be pushed to here. Okay, so these atoms will also be pushed to here. So see, up to only two bonds are broken, so the rest remains as such. Okay, the rest remains as such. Okay, so the rest remains as such. Okay, so these two plane atoms. So we have studied about dislocations in another chapter. So you can see that two edge dislocations are created, right? So what happens next? See, what happens next is that this bond, see, this tries to create a bond with each other, and this creates a bond with each other. And due to this shear stress, after that, this bond can be broken. This bond gets broken. So let us redraw it now. Here you can redraw it. So it is, so it will be two, three, one, two, four, five. This is one, two, three. This is one, two, and three remains loose. Okay, so it is three, four, five. So it is like, right. So this is how now the bonds looks like. So here there is no bond. So we are creating an edge dislocation here. So here you have an edge dislocation. That half plane of atoms is missing. That is a defect of a crystal that is called the edge dislocation. So what happens next? So this will try to form a bond here, and due to this stress, this bond will break. Okay, this goes on. See, this goes on, and this edge dislocation travels towards the right. So if I draw it completely, then it will look like this. So here it will be like this. After this, okay, and okay. So this is okay. Here it is one, two, three, four, five. One, two, finally, see, if it goes like this, finally you have a bond here, 5. Okay, so that means you have a edge dislocation at the end, and this is how this deformation occurs. Okay, so if you draw this one, so you can see that the deformation occurred up to here, right? So this is how this deformation goes. That means slip occurred in that particular plane. That means we have created a step here, a step here that is called the slip. Okay, uh, and see, if I drop the top view, then one more figure we can draw that is showing the edge dislocation. We have studied that in detail in the characteristic vectors for a dislocation. You can see that, see, up to here, slip has occurred. So in this region, you have no slip, and here you have up to here, you have slip. So that means it started from here. Okay, it started from here and proceeded towards right. You can see that this is the tangent vector. Okay, so up to here, slip has occurred. So this moves further. Okay, see, gradually, this is going further. It means this dislocation is traveling. Finally, it reaches here. Okay, I have shown only some figures, but this is how this dislocation vector travels. And finally, you will get a step-like figure here. So this is how, this is the mechanism of slip.